Okay, ladies and gentlemen, we are continuing with part 4 of our lesson on gases. Well, we were in our last session, we discussed Boyle's law, and then we had the opportunity to also look at some few examples. Um, Now, what we didn't do is we did not look at the kinetic theory explanation of Boyle's law. All right. There is a way we explain Boyle's law using kinetic theory. So I believe that is going to be a session today. All right. So let's continue. I believe that Dennis is online with the lesson. And Dennis, you have to critically assess the lesson very well because I know that Shika will be calling you for further explanation soon. Okay, so we have said so many things about Boyle's law, and so we want to proceed. You see, with this theory, we just need to assess things in a bit. For instance, the pressure. Okay, we said earlier that the pressure is the number of collisions made per second on the walls of the container by the gas molecules. Okay, so since the temperature is constant, we expect that the kinetic energy remains the same and the number of molecules is also constant because the mass is fixed over here. So I believe we are all on board. Michael, make sure that your son is with us. All right, let's continue. When the volume is decreased, I mean the volume of a gas. So when the volume of a gas is decreased, um, the distances through which the particles will travel through before striking the walls of the container also decreases. I know it's a lot to take in. Let me repeat that slowly. I just said that when the volume of the gas is decreased, or when the volume of the gas decreases, the distances through which the particles will travel through before striking the walls of of the container also decreases. So the number of collisions made per second on the walls will also increase. Okay, the number of collisions made per second on the walls will increase, which results in an increase of pressure. Again, the same number of particles will strike the smaller area and the pressure will increase. Now, when the volume increases, the temperature and the mass remains constant. Okay, so when the volume of a gas increases, the temperature and the mass remains constant, and the same number of molecules will have to travel through greater distances with the same kinetic energy. Hence, we could say that the number of collisions made per second on the walls decreases and the pressure decreases. So the number of collisions on the wall decreases, the pressure of the gas also decreases. Okay, so having said that, let us proceed to Charles's law. And before we do that, if Franco is with us, please get Mahama to join this lesson. I wonder where she may be by now. All right, so let's proceed. Charles's law. Now, we said earlier that Boyle's law is basically concerned with the relationship between pressure and volume of a gas. In this case, Charles's law basically relates the volume and the absolute temperature of a gas. Okay, so let's state it. Now, Charles's law states that the volume of a fixed mass of gas is directly proportional to the absolute temperature, provided the pressure remains constant. I'm going to say it again. It is said that Charles's law states that the volume of a fixed mass of a gas is directly proportional to the absolute temperature, provided the pressure remains constant. So in this case, we are dealing with two things: absolute temperature and volume. So with Charles's law, we have volume being directly proportional to absolute temperature. So, in accordance to our principles in dimensional analysis, we understand that to get rid of the proportionality sign, all we do is that we introduce an equal to and an equal to sign and a constant k. All right. So if you are to make this constant the subject, then our k would be equal to volume divided by temperature. So K is our constant, V is our volume, and T is our absolute temperature. All right. So yeah, so in this case, unlike Boyle's law, with Charles' law, we now have V1 over T1 being equal to V2 over T2. And this is going to be our relation for the short while. So where V1 is the volume at temperature T1, then V2 is the volume at temperature T2, we could say that the volume of a fixed mass of a gas at constant pressure expands. Since we are dealing with absolute temperature, it expands by the factor of absolute temperature, 1 over 273 Kelvin, or 273 of its volume at 0 degrees Celsius for a rise in temperature. Anyway, let's move on. Yes, so let's use these graphical demonstrations of Charles' law to explain. Now, with the graph against volume and temperature in degrees Celsius on my left, you would see how the graph extends all the way to the negative 273. But when we look at the graph of the volume against temperature in Kelvin, we realize how the graph passes through the origin. All right. So that is a graph of volume against temperature that we could describe with respect to Charles's law. Let's take an example. Okay, so we have an example now. A fixed mass of a gas has a volume of 40 cm3 at a temperature of 20 degrees Celsius. What is its volume at 30 degrees Celsius? So this is a clear relation between volume and temperature question. and this limits you to Charles's law. Okay, now we understand that the temperature that we describe using Charles's law is an absolute temperature, and that is one measured in Kelvin. So whatever temperature given to you in this example, you would have to first change them from the degree Celsius into the Kelvin. Okay, so now in our attempt, we are trying to change them to Kelvin. So changing the temperature to Kelvin, all you have to do is add the value 273. So we have the next temperature is 30 degrees Celsius plus 273, and that gives us a value of 303 Kelvin. So now that we have changed it, we now apply our Charles's law. So according to our Charles's law, V1 over C1 is equal to V2 over T2. So we are only interested in finding the new volume as to the question. So making the new volume the subject. So as to making the new volume the subject, I believe that we could have all the way here where we can make V2 is equal to say V1 times T2 all divided by T1. So when we input our values and then we do it right, we could have our V2 as 41.37 cm cube. Yeah. So yeah. So that is it. I hope we are on the know and we are good to go. All right. Thank you so much for your time. This brings us to the end of our lesson or part 4 of our lesson on gases. See you during our next video in part 5.